All right. Hello, everyone, and welcome to the 2021 Better Buildings, Better Plants Summit. I'm Josh Geyer, the multifamily sector lead for the Better Buildings Challenge, and I will be your moderator for today's session called A New Frontier, Electrification and Multifamily Housing. This session will address programmatic and technical approaches to going all electric in multifamily housing, exploring current challenges in domestic hot water, technologies for space heating using heat pumps, and more. We just a little more on that. We all know that we're trying to get to low carbon and decarbonization ultimately in the next, hopefully not that many years. And electrification is a key, indispensable part of going that direction. We have to stop using fossil fuels on site and make sure that we are getting as close to only using electricity as possible. So this is huge. It's going to be huge now and over the next several years. Next slide. Before we dive into today's session, there are a few housekeeping points I'd like to cover. Please note today's session will be recorded and archived on the Better Building Solutions Center. We'll follow up when today's recordings and slides are made available. All attendees are in listen-only mode, meaning your microphones are muted. If you experience any audio or visual issues during today's session, please send a message in your chat window located on the bottom of your Zoom panel. We will be using an interactive platform called Slido for Q&A and session feedback. Please go to www.slido.com using your mobile device or by opening a new window in your internet browser. Today's event code is #DOE. Once you enter this event code, please select today's session title, A New Frontier, Electrification and Multifamily Housing, in the drop-down menu at the top right. You can submit your questions for our panelists by submitting in Slido anytime during the presentation. You can also upvote other attendees' questions. I'll pause briefly to give everyone a chance to open up Slido and select our session. Great. If you're having any issues, please message our tech support team by using the Zoom chat function. We are delighted to have 5 panelists present their work to you today: Jordan Dentz, Andrew McNamara, Julie Klump, Rory Christian, and Edwin Mendez. After we hear from all 5 panelists, we'll end with a group discussion with all of our panelists and a final wrap-up. Next slide. To begin, I'm pleased to introduce Jordan Dentz. Jordan is Vice President of the Levy Partnership, Inc., a research and consulting firm specializing in building performance and energy efficiency. Dentz has consulted on numerous passive house projects in New York, including, in 2009, the Hudson Passive Project, the first to be certified in New York State. He has been a lead consultant with NYSERDA's Retrofit New York projects, pioneering deep energy retrofit strategies for residential buildings. Welcome, Jordan.
Thank you, Josh. And it's a pleasure to be here. I'm going to divide my presentation into 2 parts. The first part, I'm going to talk about a demonstration project that we implemented with NYSERDA to electrify 20 small single and small multifamily buildings throughout the New York City area. And the second part, I'm going to give an overview of space conditioning heat pumps, some of the advantages and disadvantages, and some new products that are coming to market that will hopefully address some of the disadvantages of current heat pump technology in certain specifically retrofit circumstances. So this demonstration project was done with NYSERDA over the past few years, and we implemented electrification of space conditioning in 20 sites. These were all 1 to 3 family buildings, originally gas and oil fired boilers and furnaces, generally old buildings with limited or minimal insulation. The objective here was to really understand what the costs were and the benefits and get some experience doing these electrifications. Partners with us on this project were, in addition to NYSERDA, Frontier Energy, did the measurement verification, and Sensible House was instrumental with recruiting and managing the sites. Next slide, please. So the scope, as I mentioned, was full replacement of the heating system with a heat pump system. Generally, these were ductless mini splits, NEEP listed, which is a cold climate air source heat pump that is designed for providing full heat in cold climates. Usually there are 3 to 4 outdoor units per building, 6 to 12 zones inside. And the clients were receiving some incentives, but they were contributing a fair amount of their own money towards these retrofits. And the reasons they were doing that is listed there on the slide. They were interested in increasing their home value, improving comfort results by providing quote unquote central cooling, and solving poor heat distribution from their existing systems. Notice that energy cost savings was not on that list. Next slide, please. So this is some data that, one of the data that we were hoping to gain from this project is what are the costs of these systems to retrofit in these types of buildings. The project costs range from a low of about $10,000 up to $50,000, and there were some incentives as well for the residents. We found that we looked at costs on two ways. One is the cost of the heat pump systems per zone, so that's per room in the house that received a indoor unit, and the other is per ton or capacity of heating. The per zone system tends to be more consistent on a project-to-project basis because that's really where the labor is. Running the refrigerant lines, putting in the indoor units, connecting them up, less so the equipment size-based costs. And so we found fairly consistent, about $3,500 per zone for these types of retrofits. On a per ton, it's close to $4,500 on average. The next slide, please. We'll show some benefits, the results of the measurement and verification. So as I mentioned, we did 20 sites. I don't have data for all 20 yet here. There are a few still outstanding. But you can see here a matrix showing by site, the original fuel for the heating and the savings in terms of energy, carbon emissions, and utility bills. Note that the green cells in the columns showing cost savings are positive savings. In other words, they're paying less post-retrofit. And the red, the customers or the clients are paying more after the retrofits. It's important to understand the reasons for that. The first thing that jumps out is, of course, natural gas is inexpensive. And so the oil sites tend to have positive savings and the gas sites tended to have negative savings. But the other reasons relate to behavioral changes and indoor set point changes. Once you're now space conditioning and space cooling more thoroughly and consistently throughout the home, there could be an increase in energy use there. But all the sites did save significant amounts of carbon because the emissions related to that electricity is lower than the fossil fuels that were being consumed prior. Changes to the price of energy, of course, will make a dramatic difference on the relative savings and lack thereof for these retrofits. We also looked at an estimate of what the efficiency of these units were, and those are the columns to the right. COP counting for envelope would be an estimate of what the efficiency was, and they're somewhat disappointing in that we're hoping for COPs closer to 3. COP stands for coefficient of performance. And we got some coefficients of performance that were closer to 2, in some cases lower. Again, that could be related to some of those behavioral changes and an increase in heating or cooling that was behavioral related. So there's still some work to do there to ensure that the systems are operating to their maximum efficiency. So those are some of the high-level results from that study. There'll be a full report on that project coming out later this year or early next year. Go to the next slide and the next part of the presentation. So I want to just give a kind of an overview of space conditioning heat pumps and then talk a bit about some new technologies that are in the marketplace. We're talking strictly here about electric heat pumps and really focused on air source heat pumps. Of course, our ground source heat pumps, which are appropriate in certain cases, but air source heat pumps are easier generally and applicable to more buildings. Divide that into both. We can divide air source heat pumps into package systems in which the entire heat pump is in one box versus split systems where you have an outdoor unit and indoor unit. And furthermore, the split systems can be divided up into large central systems where there's one system that's serving an entire building, commonly called a VRF system, or individual systems like the mini splits we installed in the previous project I described. There can be anywhere from one to a small handful of indoor units connected to each outdoor unit. So I'm going to go to the next slide, please. So why heat pumps? Why are heat pumps beneficial for electrification? Why are they so important in our efforts to decarbonize? Heat pumps today can meet full heating and cooling demand in almost all climates for almost all buildings. They're efficient when installed and operated appropriately. They're reliable, comfortable, quiet, and there are a lot of options out there. Next slide, please. But there's still some drawbacks to heat pumps, which is kind of holding them back, particularly in retrofits in existing buildings. Of course, you need electrical. There's a list of some of those drawbacks here. Electrical service requirements generally are going to be higher for heat pumps than buildings with boilers or furnaces. There's labor to install them, which is significant. The installation for existing buildings can be intrusive if you're installing refrigerant lines around the building. There's a fair amount of design work that goes into them and has to be done well. As I mentioned, the refrigerant lines also can be aesthetically unpleasing, and there are potential leaks that could be leak refrigerants that have a negative impact from an emission standpoint as well. You need to find places for the outdoor units, but of course you don't want to clutter up your roof with them if you want to put solar on your roof. So there's a bit of a conflict there. Let's go to the next slide. So we're going to talk about 4 new heat pump products that have come to market that can address some of these challenges. And this is just a sample of a few examples. There are other products out there, and the market and technology is evolving quickly. Next slide, please. This is a new heat pump that is from Italy. It's called the Epaca HVAC 2.0. And there's a couple of products similar to this out there as well. But it's basically an indoor unit that hangs on the wall with 2 pipes that go through the wall. So there's no outdoor unit. This would be a package system. But it contains the same technology that you have in mini splits. So it meets those efficiency levels, the VRF compressor, the variable efficiencies compressor, variable speed compressor, and fans, and sophisticated controls to achieve those same high efficiencies and capacity at all outdoor conditions. There are no refrigerant lines to run. There's very small wall openings. Next slide, please. There's a few more images of other alternative ways that this could potentially be installed as part of a retrofit in conjunction with windows, perhaps. Next slide, please. And we project that the cost of this installation could be as little as half of what a VRF system, a typical split system, might cost. So this is the really potential. This type of product has a potential to be a game changer for retrofits. Next slide, please. The next product I want to mention is a mini split that fits into a PTAC sleeve. Next slide, please. So there are many buildings around the country, both residential and hospitality, that contain PTAC sleeves. We have through wall units. And this is an example of a building in New York on the right. On the left is a building not in New York, but this is one way you can get mini splits onto a building such as this. But if you go to the next slide, we'll see another option. This is something that Fujitsu is coming out with this year. And again, there's another manufacturer coming out with something that's very similar. I think it's already in the market, by Gree. But this product slides into that same sleeve. It's basically a mini split that has more of a cubicle configuration, and you would connect it to an indoor unit such as shown on the left. Next slide, please.
Jordan, you have about a minute and a half.
Okay, I'll get a bit quicker then. Then you close it up and that's what you got. Next slide, please. So we get a comparison looking at the Fujitsu unit to other alternatives. It does cost more, but given the efficiencies, the net present value of that installation is quite a bit better than those alternatives. Next slide, please. Does it belong? This product is a mini split that plugs into your hydronic distribution system. Next slide. Oops. This is a heat pump that can plug into a building that has a hot water heating system, and you don't have to go into any apartments. You can just plug it in where the boiler was, and it'll provide that hot water. Again, this is a new product also from Italy to provide another alternative for that building type. Next slide, please. So this is a schematic of how that would work. There's 2 parts to it, and then it goes to the existing hydronic distribution system. Next slide. And the last product is a heat pump that pops into your window. Next slide, please. It's basically a window unit. Does not block the window. It's kind of a saddlebag type approach. This is a company called Tro out of California. It's got all that same VRF technology built into it, expecting it to be a mass market product. And at the same efficiencies of the mini split, it can provide heating and cooling very inexpensively installed. Next slide. This is an example building that we've analyzed with all 4 of these products. Just bottom line is they're all saving carbon based on their efficiencies, but it's very challenging with the energy rates that we have today, at least at this site. This is a New York City rate, to reduce energy costs compared to natural gas. So that's still a challenge. Next slide. Just a few other products that are also, these are very similar. A lot of products coming out with this VRF technology. So more options coming out every day. And I think my last slide is coming up. That's all I've got. Thank you very much. Hope I hit the time.
Thanks, Jordan. Heading right on to our next person, which is Andrew McNamara, Bright Power's Executive Vice President of Operations in California, leading the company's California operations. Since joining Bright Power in 2006, Andrew quickly rose to Vice President in 2008, leading the firm's sustainability and solar practices from 2008 to 2013 and the engineering division from 2013 to 2015. He has worked on hundreds of projects from coast to coast, including over a dozen heat pump water heater electrification retrofits in California. Welcome, Andrew.
Great, thanks, Josh. And hello, everyone. Great to be with you today, talking about multifamily electrification, such an important topic. And what a great presentation by Jordan on heat pumps for space heating. Just to draw a distinction, the focus of my presentation is heat pumps for domestic hot water and making sure that we deliver those vital hot showers for multifamily residents. On the next slide, we have a brief overview of Bright Power. My role is to run California operations based in sunny Oakland, where I'm speaking to you from today. And on the next slide, just a quick overview of Bright Power's approach. We act as an energy and water management partner for real estate organizations, basically a one-stop shop that can take an owner from not knowing where to start through completed projects. And electrifying domestic hot water is just one thing we do alongside a host of other technologies like lighting controls. And our mantra is find, fix, follow, to find energy, water waste, and find, fix it, and follow that through. Moving on to the next slide, as I get into content here, I want to ground us in the diverse perspectives surrounding heat pump water heaters. There are so many important stakeholders in the conversation, and we've put 3 of the big ones on the screen here. We often hear from policymakers who want to incentivize the market to scale up and meet carbon saving goals, from property owners who want to make sure their residents will actually get hot showers and want to make sure they have a project that pencils. And then the industry wants to know how many calls they're going to get for complaints and if it's worth building a business around this technology. And so let's remember these perspectives as we go through this presentation. Moving on to the next slide, we have some technologies for electrification. As I said, my focus is on the first line here on water heating and heat pump water heaters. But this slide shows the context of other technologies for space heating, as Jordan shared, as well as for cooking, clothes dryers, and pools, which is outside the scope of this presentation, but important as well. Moving on to the next slide, we segment the heat pump water heater technology into a few different buckets. So first, we can look at residential, single family, integrated tank style, as well as split systems. And there's these tiny little photos just to give you a little sense, but these are the integrated tank would be your drop-in replacements for an existing tank-based water heater, as well as split systems, which are similar, except they have an outdoor condenser style unit. Then on commercial, you have more low-rise targeted products like an integrated tank, as well as residential manifolded. And then what I've labeled as high-rise, although it could also be useful in campus style installs where you have large split style systems. Moving on to the next slide, here's a timeline of Bright Power's multifamily heat pump water heater installations to date. And we're so honored to have worked with visionary owners like Mercy Housing, Jonathan Rose Companies, TNDC, and others on pioneering heat pump water heater retrofits at their properties. We started in 2017 with our first installs with Mercy and have installed heat pump systems serving over 1,600 bedrooms at 16 properties. Moving on to our next slide, we segment our installations into a couple different categories. The first generation were the residential style Sandin units, which we'll get into photos of in a moment. And then the second generation were the Colmac and Nile, are the Colmac and Nile style installations, which are more of a single central unit. And then you can further segment those into heat pump water heater only and hybrid installations, which we'll get into over the course of the presentation. This the heat pump water heater only versus hybrid, basically the concept there is we'll share projects which are retrofits here in this presentation where existing boilers were already present on the site, right? So in the hybrid configuration, we leverage a gas boiler, usually the existing gas boiler, as a peaker plant to reduce the required heat pump capacity. Whereas in a heat pump water heater only configuration, there's no natural gas backup, and we have some experience with both. All right, so enough on context. Let's look at some installs. And moving on to the next slide, in 2017, the journey begins. And on the next slide, our first installs were utilizing Sandin heat pump water heater units. And what we did here is manifold together the Sandin units, which are pictured there, about the size of a large suitcase. It's really a single family product to serve, and we manifolded them together to serve the multifamily market. So this is a 90 unit property you're on the roof of. And there's 9 Sandin units manifolded together and backed up by the gas boilers, which you can also see in the background of the left-hand photo. We did installations similar to this at a total of 7 properties ranging from 36 to 151 units. And this work was funded by California's low-income weatherization program. And we were honored to work with our partners at AEA, the Association for Energy Affordability, and also CSD on making these installations a reality. On the next slide, you can see the technical specs for our installations. I'm not going to go through this point by point, but these are split systems. The CO2 refrigerant has a low global warming potential, which is a really nice feature of the Sandin units. And the rated COP of 4.5 is really strong, but maintaining that in practice takes some really strong applications engineering, which we'll get into a little bit later. Moving on to the next slide, a little bit more detail on the technical specs, which we'll move past quickly to get into photos. And on the next slide, you can see one of the reasons we picked the Sandin technology for these properties in San Francisco is that it fits into tight basements. So here you're on the back side of the boiler room and those Sandins are mounted on the wall and they operate really quietly. They actually are blowing cold air out of them. They fit into tight basements and boiler rooms in the urban core of San Francisco. On the next slide, you can see another property on the same portfolio where we mounted the units in a breezeway adjacent to the boiler room. Still plenty of room for clearances to walk by. And then on the next slide, you can see a key design consideration. So COP is the operating efficiency or the coefficient of performance. And if the COP drops below about 3.6 in PG&E territory, the heat pump water heater will actually cost more to operate than the boiler it replaced. And one of the keys to achieving the target COP is managing the inlet water temperature. And if your property has problems with crossover flow or other distribution issues, the inlet temperature to the heat pump water heater can rise if it isn't properly managed and the efficiency can plummet. which increases your costs, your operating costs. And this was a key lesson learned from our early installations, is managing that in existing properties. Moving on to the next slide, you can see a financial illustration. There's a lot going on this slide, but the orange line represents your break-even COP. So that's where the heat pump water heater at this particular property would cost the same to operate as the pre-existing natural gas boiler. And you could see that if you don't manage your COP effectively and you end up on the blue line at a lower COP, you could end up paying, upwards of $5,000 more per year to operate that heat pump. And that's where managing that COP and making sure you have strong applications engineering and good troubleshooting, because a lot of times these issues crop up during the commissioning period, is really important. Moving on to the next slide, you can see a typical system schematic for our Sandon systems. And I'm not going to get into detail here today, but on the next slide, you can see kind of an overview of those distribution issues in a flowchart form of how existing property issues of crossover flow and recirc imbalance led to needing to operate the recirc pump constantly to avoid complaints. That was the maintenance staff response, which led to the heat pump tanks destratifying, which led in turn to return water temperature that was higher, a lower COP, and higher operating costs. So on the next slide, we get into lessons learned, and I don't have time to address them all in detail today, but really, number one, I mean, the technology really worked, right? On these first installs, we were able to reliably deliver hot water after working out a lot of kinks, due mostly to number two, that heat pumps are not boilers. You got to design them differently and require special applications engineering. And number three, which was, the challenges related to those existing buildings I just addressed. And on the next slide, number six is such an important one, that hybrid systems, where a natural gas-fired boiler is utilized alongside the heat pump is really a wonderful transition strategy to maintain uptime and reduce upfront costs. Moving on to the next slide, coming out of our 2017 and 2018 installs with the Sandon systems, we installed our largest system yet on a Los Angeles high-rise called Casa Panorama. It was amazing to work with our visionary partners at Jonathan Rose Companies, and the project received substantial incentives and technical assistance again from the Low-Income Weatherization Program, and thanks to AEA and CSD. Moving on to the next slide, here are the technical specs. We used a Colmac HPA15, which is 17 times the size in terms of capacity of an individual Sandon unit. So no more manifold of many units tied together, and a hybrid plant design where we reused the existing boiler. And the heat pumps were designed to cover about 90% of the annual domestic hot water load. Moving on to the next slide, and onto the fun stuff. Here you can see our crews on site as we craned the heat pumps into place. And on the next slide, you can see our friends from Colmac, the manufacturer, doing startup commissioning on the heat pump. And on the next slide, this shows the pre-existing boiler and storage tank, which we reused and which act as the gas peaker plant. It provides about 10% of the annual load, but it's there for those rare moments when everyone happens to shower at once, and really helps to keep the cost down, because a lot of capacity that you pay for in your water heating system is just there for safety factor, right? And so the safety factor is basically taken care of by these units. So the expensive heat pumps can just cover the base load. On the next slide, here's a schematic design with the Colmac system. The design is streamlined with many fewer points of failure than we saw in the large manifolds of our earlier Sandon systems. And on the next slide, we show another Colmac installation we performed in San Francisco at a TNDC property. Again, this project was funded by LIWIP, and the four photos on this slide show the progression of installation from a pre-existing gas boiler to a final heat pump. And shout out to my project management and engineering teams, Jeff Teigen and Amy Nagengast, who worked with the crews to get hot water back up the same night when we needed to get all this equipment out of a tight room and all the new equipment installed. Moving on to the next slide.
And you have about 2 minutes left.
Great, thank you. Zooming out from the particulars of installations, I'd like to briefly discuss what I see as the path to domestic hot water electrification from an ideal policy perspective. For single family and unitized multifamily domestic hot water systems, we're really ready for heat pumps now. And as I see it, the vast majority of end of life replacements ought to be heat pumps. For multifamily central systems, I'd encourage us to facilitate hybrid installations, particularly over the next 3 years. And the reason is that we can get 90% of the gas offset, 90% of the carbon reduction for about 40 to 60% of the cost. And we can do so reliably, so we don't give the technology a black eye. Really, every one of our installations that we've done to date has brought new lessons learned. And it was so valuable to have a safe place to work through those lessons learned. And furthermore, hybrids can go in many places that regular systems cannot, where you run into electrical capacity issues, or maybe there's no ventilation to get rid of the cold air that the heat pump water heaters produce. So while I think hybrid installs should be the mainstay for the short run, we should also look for Goldilocks properties that can go all electric now. Ones that are verified not to have distribution issues, have sufficient electrical capacity, and satisfy many other conditions. So on the next slide, to sum up my perspective, we got to follow the model of the Toyota Prius to move from gas to electric, and do the hybrid installations to start before moving on to the all electric over time. And on the next slide, just quickly show some cost data showing in orange our heat pump water heater only installs, and in blue our hybrid system. So you can see this represents about half the cost per bedroom installed when we're doing the hybrid installations. And on the next slide, in closing, I'd like to end with a message for those who are wondering, how do I get started with all this? And my recommendation for you is to get your feet wet now first. In a few short years, policy may force you to install heat pump water heaters at your properties. Wouldn't you rather get started with your design teams and staff exposed to the technology now on your terms and while you're in control? Second, for retrofit projects, look for partners that can bring a design build approach. In my opinion, there are just too many nuances that crop up during the course of a retrofit to make a separated design and installation process really workable in most circumstances. Third, seek areas with strong incentives to find projects that pencil. California is a great place to start with programs all over the state. And last, on new construction, consider cutting out gas of your project altogether. Studies have shown the savings of avoiding gas service and piping can more than cover the premium of installing heat pumps. And the technology works great in new construction. I actually personally live in an all-electric home, and showers are hot, and I love my induction cooktop. So with that, thank you for your time and attention, and please reach out and start a conversation with us.
Thank you so much, Andy. All right, moving on to our next speaker. This is Julie Klump, Vice President for Design and Building Performance for the Preservation of Affordable Housing, POA, responsible for design and energy efficiency of development projects and the owned portfolio. She assists POA in the building acquisition process and works with POA's development project managers and asset managers to rehabilitate new acquisitions or POA-owned properties. Julie is a certified passive house consultant and a LEED certified architect. Welcome, Julie.
Thanks, Josh, and thanks for the invitation to the panel, and thanks to everybody that joined us this afternoon. POA is making some real strides and towards electrification with our commitment to decarbonization. And we know that electric grids are not perfect in how they make and provide electricity, but we're trying to get ahead of the net zero curve and try to really improve our enclosures and get rid of fossil fuel at our properties. Next slide. So just quickly, where POA is located, we have 12,000 units in 11 states and DC. And as you can see from the map, we're in just about every climate zone. And that sort of makes life interesting when you're trying to incentivize energy upgrades and also install them. And to add, we're a bit obsessed with data. We use a third party to process all of our utility bills and create accounting files, which gives us raw utility data. And we use a couple energy platforms to weather normalize the data, show us anomalies, show us the impacts of our rehabs and discrete water, energy and water savings projects. Next slide. So this is what we're up to. I'm just going to talk quickly about new construction. Everyone's heard about ambitious carbon neutrality goals in cities across the country. And I think getting there with new construction, it's sort of the baseline should be passive house. Nearly all of our new construction projects are designed to be passive house certified. We have 1 in construction right now and 6 in design that we're committed to certifying. And I highlighted on some of these, you can see that they're not all electric. Some of these buildings are in locations where the disparity between gas and electric just creates such a burden for our operations that we've had to make the choice to use gas domestic hot water. Andy, I'll be calling you to talk about heat pump hot water heaters because I'm eager to get them into our properties, and the properties here that say 100% electric are actually, that's what we'll use for hot water. One of these projects is actually, and the ones that aren't designed all electric, we're at least designing the hot water systems that can easily be converted to domestic to electricity. Next slide. So I think what new construction passive house, we ensure robust enclosure, we get to low load heating and cooling demand, which makes it really easy for electricity. We use all electric ventilation systems. Domestic hot water is a question mark depending on where we're actually building. And backup power, we have one building in Boston that is all electric. It has a battery that's designed for backup power. And we're looking at offsite renewables to just fill a small gap that the rooftop array won't cover in order to get to net zero. And the barriers for us in some locations, as I mentioned, is just the cost of batteries and also the cost of gas versus electricity. Next slide. But we have more existing buildings than we do have the opportunity to build new. When I started at POA, all we did was acquisition rehabs. And I think I've been in some committees in Boston for their carbon neutrality goals, and everyone pushes the passive house on the new construction, which I feel like is kind of it's becoming more and more a no-brainer. But what about the existing buildings and what about historic buildings? And so when I started at POA, what the lenders wanted to see is how many kitchens and baths are you going to rehab? And nobody wanted to talk about energy efficiency unless there was some incentive to do something with it. And before that, we were even converting electric resistance heat to fossil fuel gas, boilers and furnaces. And so we've come a long way. As early as 5 years ago, we've convinced a lender to let us improve the enclosure over kitchens and baths with the argument that we can't replace windows during unit turns. And we just feel like if we can get the enclosure right while we have a bite at the apple, we can ensure durability of our buildings, we can create healthier housing, we can save energy, and we can also provide some resiliency. Next slide. So ideally our retrofits, we update the enclosure whenever, especially when new cladding is needed. We've done foam injection on some projects where it was masonry cladding, which is another way to beef up your enclosure. We convert to electric heating and cooling. All of our ventilation is recovery with, that's all electric. Again, domestic hot water, we're still working that. And again, backup power. And then I think the big issue for us on converting to a heat and electricity, which people can probably relate to, is that if you don't invest in a robust enclosure in a northern climate where the heat, the design degree for heating is well below zero, you might not be able to accommodate the loads, the heating loads that your buildings and residents want without with an electric heating system. You at least lose a lot of the efficiency of that heating system. Next slide. So I'm going to talk quickly about one project that I'm super excited about. This is a 283 unit building in Salem, Massachusetts, which is north of Boston. It's two 10-story towers built in 1973. Fortunately for the energy folks in my office, the bricks are not stable. In 1973, building codes allowed you to build brick cladding systems that literally support themselves from the ground up with a few brick ties holding them back. Well, the brick ties are all rusted, and so it's time to reclad. So what we're going to do here is improve the enclosure. And about a year ago or 2 years ago, the utility paid for an entirely new heating and domestic hot water system that is fossil fuel. So let me tell you what we're going to do, and you can see how we hopefully will eventually not even need that system. Next slide. So you can see on the far right the existing enclosure. It's brick. There's cavity insulation. And that's about it. What we're going to do is we're installing Armor Wall, which is a structural insulated panel over the studs. And then we're going to have an open rain screen with aluminum panel. And what the Armor Wall gives us, it's a built-in air and water barrier. And it also allows us to attach the cladding with a thermally broken cladding attachment. We're installing new triple pane windows that have pre-manufactured jam sill and head extension, which makes the details really clean and easy to install. And you can see the roof on the left. We're installing 6 inches of insulation. So we're really beefing up this enclosure. Unfortunately, I've been told it would take 50 blower door tests and probably 100 people in order to do blower door testing at this building. So we're not going to be able to do a pre-blower door test, but I'm really counting on some really robust improvement there on air tightness. The gas savings, we've modeled what that savings for that system, and it's about, it's just under 20% for that. We're expecting between the enclosure and some of the other upgrades that we'll be at 60% better than we currently spend at this building. Next slide. So on the theme of new technology for heating and cooling and ventilation, we looked at rooftop units that would distribute heating and cooling or ventilation air to the units through ductwork down the hallways, which would have eliminated, which would have added ventilation, but we still would have had to keep the cooling system that was there, which is basically a through wall unit. So what we landed on was we landed on a Minutair unit, and some of you may have been introduced to these systems at energy conferences, but basically it's heating, cooling, ventilation in a box. So we're building a closet on the exterior wall. We're installing the Minutair. We have an exhaust and supply that go to the exterior, high and low, and then we're creating soffits that will sort of disguise and will conceal the ductwork. There's a lot of asbestos in the sheetrock, so we're having to do everything below the ceiling. So I think you can sort of see that in the AXO and the drawings. We did an install in in the property management office, which was a former unit. And after 3 or 4 months, it was really, it didn't help. I mean, it didn't hurt our conversation with pursuing this because the staff were just they couldn't believe how fresh the air was, how quiet the unit was, and how easy it was to control. Next slide. So, as well as the Minutair system for heating, cooling, and ventilation, the existing heating system that will supplement the Minutair when the heating can't be met by that. We are also, we have in our base budget to do a wall-mounted PV system on the south wall of this building. We need probably 200 kWh or kW per year. So this will be half the energy that we need for electricity. If we do the rooftop, which we hope we get to do as well, we'll be way over what we need on the electric side. And so hopefully if our enclosure can allow the Minutair to provide the heat and we don't need the heating system, the fossil fuel system, we'll just have to tackle the domestic hot water.
Julie, you have about 2 minutes.
Okay, perfect. Next slide. So how close are we? We're like I said, we're just hoping the Minutair can accommodate the heat, which we'll see, we'll start to see next year. I look really forward to sharing the results of this maybe next year. Next slide. So just really quickly, I'll talk about some historic buildings because I think they provide some real challenges given the historic oversight for upgrading enclosures. This is a building that it's 2 properties that we've just acquired. Obviously, a lot of 3-way structural masonry walls, and then there's one that has wood cladding. The wood cladding one is a little easier. We pull the wood off. We do exterior insulation over. Everybody gets a new window. They're not great windows, but they're good windows. Just because of the historic constraints. Next slide. The exciting thing here that we're doing is as a way to minimize refrigerant in our buildings is we're going to install the Mitsubishi hybrid. So it's basically a VRF unit with refrigerant that runs to, let's call it this is calling it a branch controller. And from the branch controller, it becomes hydronic. So in each unit, there's a vertical fan coil, which is not unlike what they have now. So distribution of cooling and heating in the units will be the same, but we've minimized refrigerant. We've gone to all electric. And so we're super excited about this. It comes with a heating booster that we're going to install mostly for the masonry buildings because we're not quite sure without a robust enclosure upgrade there that this will be able to accommodate the heating with the efficiency that we want. So gets rid of the through wall ACs, which maintenance likes and the Historic Commission likes. So next slide. So we obviously haven't solved for all our loads in terms of the ones that use fossil fuel, but we're psyched about better technology that's coming out in domestic hot water and economics for solar storage. But with that, I'll say thank you, and I look forward to questions.
Thank you so much, Julie. Now we move, last but not least, to Rory Christian and Edwin Mendez from the New York City Housing Authority. Rory is principal of Concentric Consulting Group, focused on the intersection of energy efficiency, environmental justice, and affordability. He previously led the New York Clean Energy Program for the Environmental Defense Fund, and prior to EDF was energy director at NYCHA, where he spearheaded NYCHA's efforts to integrate and standardize energy performance contracts in the capital planning process. Eddie Mendez has worked with NYCHA's energy department in a variety of roles for 15 years, where he managed the installation of NYCHA's first remote heating management system. Currently, Eddie oversees more than $300 million in energy efficiency program construction, including energy performance contracts, weatherization assistance program, and retrofit NY projects, and electrification pilots. Welcome, Eddie.
Thank you, Josh. So I'll kick things off and I'll transfer over to Eddie about halfway through. The presentation I'm going to share with you today documents a little bit about NYCHA and the pathways that we've developed towards our decarbonization goals. So we're going to be talking about a portfolio approach to addressing these issues that's going to incorporate many of the different technologies and applications discussed thus far today. And before I go on, I want to wish everyone a good morning, good afternoon, and thank everybody for being here. So as you can see from this slide, NYCHA is the largest landlord in New York City, and by many counts, possibly the nation, second only possibly to the US military. We are a major economic driver of the city of New York, with over 500,000 New Yorkers calling our either public housing or Section 8 housing home. Almost 80%, actually more than 80% of our families are fixed income, with about 13% receiving public assistance, and 40% of our families are headed by seniors 62 years or older. NYCHA housing is prized and it's hard to come by. We have a turnover rate of roughly sub 3% turnover rate and a vacancy rate of roughly 1%, and a waiting list of roughly 300,000 families long. So ultimately, there's a strong need to make sure that our housing is maintained and continuously available. And right now, when we evaluate our capital needs, they're roughly in the ballpark of about $40 billion simply to replace in kind. So we haven't even begun the conversation on what it would cost to upgrade. And so now I'll get into that. Next slide, please. So this is just a small overview of some of the many reports that NYCHA has put together over the last few years, documenting a variety of challenges and opportunities we face in addressing climate change. One of the underlying most important parts of our plans, we want to improve the quality of service to our residents and the overall condition of the building stock. And much of what we have come up with is with those two considerations in mind. Now, the climate mitigation roadmap, which you see front and center, was developed over the last several years and examines options for NYCHA to reduce emissions by 80% from prior levels. We're talking from a starting point of about 8.7 metric tons of CO2 per 1,000 square feet, with a goal of achieving around 1.7 metric tons CO2 per 1,000 square feet. So this plan outlines a pathway to achieving that and rests on the foundation of NYCHA's 25 plus years of experience pursuing energy efficiency work, much of that by Eddie, myself, and our peers and collaborators. Now, through the passage of Local Law 97, that threshold, that 1.7 metric ton CO2 per 1,000 square feet threshold, has been established for NYCHA buildings over 25,000 square feet. This is not a instantaneous requirement, it's the end goal. So over the next 20 to 30 years, NYCHA must move forward, reducing its emissions from that 8.7 figure to that 1.7 figure by 2050. Now, this is a difficult process for the owner of a single building, as you've heard from our prior presenters, but for NYCHA, the scope and scale is a little bit different. There are roughly 1,300 plus buildings under ownership by NYCHA. And when you think of that number and the goal of doing this by 2050, that's a little over 40 buildings a year, every year for the next 30 years. Massive undertaking. Next slide. So we put together these plans in part to make it clear the significance of the undertaking NYCHA must move forward with. Thing to keep in mind, they're not static. They are far from monolithic. They're simply considered a pathway based on available technology, funding mechanisms, and laws that NYCHA can move forward with towards achieving its goals. The new approach, aligned with broader national and state efforts, leverages 21st century technology and practices. And if NYCHA is to achieve the reductions required in the time allotted, what we're about to present to you today takes into account what's commercially available best practices towards doing so. Josh, next slide, please. So what we have here is business as usual. This is simply, continuous retrocommissioning, replacing boilers of kind, steam system optimizations. And if you can see at the bottom, each column represents a stepping stone along the path towards what an emissions reduction pathway could look like. The first column is the 2005 baseline, showing the 8.7 metric ton CO2 per square feet, 1,000 square feet. And then our reference here is 2007. And then the first strategy is, again, retrocommissioning. Strategy 2, energy performance contracting. But again, all of these approaches are replacing equipment in kind. And what you'll note as we move forward with each of these tried and true tested approaches, and this is not the full $40 billion in scope that I mentioned earlier, the best NYCHA can do is achieve the 2030 goal established by the City of New York of 5.1 metric ton CO2 per 1,000 square feet. So if we continue doing what we've been doing, we'll certainly make some significant reductions, but it'll be far below the target goal of 2050. So what does that mean? We can continue investing in these infrastructure upgrades to maintain quality service, but in reality, we need to consider an entirely new approach that redefines what NYCHA's done historically and prepares us towards meeting that 2050 goal in the future. Next slide, please. So we look at this in two parts. The main thrust will be examining basically our heating and hot water. And the second part of it will be looking at in-unit energy consumption and understanding what we can do to address costs associated with unmetered resident consumption. Ultimately, when we look at these two things, they're all dependent on the state's current plans to decarbonize the electric grid. Right now, the grid is cleaner than it has been in ever, some would argue, but it stands to get significantly cleaner over the next 30 years. And the improvements we have planned will piggyback off of those state level initiatives, thus accelerating the pathway towards that 1.7 number mentioned prior. Next slide, please. Now, if we were to do that, here is a scenario that, again, is contingent upon grid decarbonization, where we can actually achieve the 1.7 metric ton CO2 per 1,000 square foot number. And what's interesting about this is this need not be done to the entire portfolio. If we look at strategy 1, which is hot water electrification using some of the methodologies discussed in prior presentations, if we were to apply that to the entire building portfolio, you see we get a very significant reduction in emissions just from that alone. Strategy 2, adopting air source heat pumps, And again, this would be done, I believe, at roughly 60% of the portfolio. So this need not be done through all of NYCHA, just the buildings where it's most feasible, the Goldilocks building, so to speak. We get another significant chunk. And then finally, we continue doing retro commissioning and energy performance contracts. This is strategy 1 and 2 that we mentioned in the prior slide. So electrification need not be the sole driver, but it will be the key driver towards achieving these goals. Because as you can see in the last column, once we do the hot water and the space heating for strategies 5 and 6, as the grid gets cleaner, we get even greater benefits as we move forward. So I'm going to stop there and pass it on to Eddie, who will talk a little bit more about strategies.
Sure, thank you, Rory. So I'll focus on implementation of some of the items that Rory had mentioned. So NYCHA is diverse in our portfolio. As Rory explained, the size of our portfolio is quite large, and we understand that what may work at a 6-story building will likely not work at our 20-story tower in the park type buildings. So many of the electrification methods and scenarios that the other panelists have discussed are all being looked at here at NYCHA to further electrify our buildings, including the VRF systems and packaged thermal heat pumps. Next slide, please. This is to reiterate the point that for us to achieve the carbon emission reductions, whatever scenarios we choose, it has to include electrification of our heat and hot water systems for us to achieve those goals. Next slide, please. So here I'll get into some specific projects that we have going now. One of them is an R&D project in which we're partnering with both NYSERDA and NYPA to develop a window unit heat pump. We see this as a great game changer in that we could electrify our heating systems by just like installing a unit similar to an air conditioner. And this would be a great benefit to NYCHA. They could be installed in emergency situations as well. Next slide, please. So here is we're not gonna, as that, as that unit is being developed, we're still moving forward with electrification at our buildings. In particular, we have targeted our first complete building for electrification. This building happens to have AC sleeves that we can use current existing through the wall heat pumps that can be placed in there and address the heating as well as cooling. Identify a method for hot water electrification, and then install induction stoves, so NYCHA will have its first all-electric building. Next slide, please. And lastly, we realize we can't just focus on the heating and cooling systems, but we need to work on our envelopes as well, as that'll assist us in our electrification methods, looking at systems as panelized cladding or EIFS. And we currently have a building as a part of the NYSERDA Retrofit New York a program that is in design for a panelized cladding and electrification upgrade. Thank you.
Thank you, both of you. Thank you to both of you and all 5 of our panelists. We're going to open up the floor for a group discussion with our panelists. So I'm gonna pitch some questions that are primarily to one of you, but any of you can then chime in. So the first is to Jordan. Jordan, how do you account for the air change requirements for a heat pump water heater compared to electric resistance water heaters in an apartment?
That might be for Andrew. It's about water heating.
Oh, interesting. The air change. So, okay, yeah, I guess so. Yeah.
Sorry, could you repeat the question?
So there's a question about how you account for the air change requirements for a heat pump water heater compared with an electric resistance water heater in an apartment.
Yeah, it's a key design consideration. So every heat pump water heater makes the air around it cold, and you've got to manage that cold air. It really, the way I look at it is you should always start with creativity and trying to find the easiest pathway to reject that cold air. Sometimes we've located the heat pump water heaters in a boiler room where there's tons of extra heat already. Sometimes we've located them near a trash chute where there's a lot of fresh air coming in anyway, fresh makeup air. And, you know, sometimes in a unitized scenario, it's as simple as putting on a louvered door if that is in a place where the cold air can be exhausted efficiently. So it's just, but it's absolutely a consideration, and sometimes it's more challenging than others. The worst was in a downtown San Francisco environment where exhausting the air, we ducted and created a noise issue and had to come back and retrofit that with a VFD fan that operated more quietly. So just, you know, there's no cookie cutter answer. I think, you know, there's just a lot of different cases that you run into in retrofits.
So I'm gonna, the question just came in the chat that I think is for either Jordan or Andy, or both could take. So what are the benefits to a heat pump in a box versus one that's split?
So a heat pump in the box, I assume we're talking about a package system. And the main advantage there is ease of installation, lower labor costs. A split system requires a place to put the outdoor unit, maybe on a roof or a balcony or on the ground. And run refrigerant lines to connect them to an indoor unit. That's labor intensive, it's disruptive. There's also the risk of refrigerant leaks. The advantages of a unitary or a package system is it doesn't have any of those disadvantages. You do potentially need more space in the apartment. You're going to have a penetration in the wall for air exchange. But those are the main considerations. That's the main advantage of the package system. And now the package systems are coming out that have similar efficiencies. If they perform as well as they're supposed to, then there could be some big advantages there.
Julie, so you talked about one of these. Do you have anything to add to that?
You know, we have it installed in one unit. We're about to install it in 283. All we've heard is that it's comfortable. It, you know, it does minimize the refrigerant, and I think the unitized system is also something that people think about in terms of air crossing and, you know, in a more central system. So I'm looking forward to results.
So I think this is primarily for Andrew. So but others please chime in. Electrification usually requires either electrical service upgrades or much more complex logic and controls that spreads load and use timing. Could one of the speakers please address this challenge to scaling electrification?
Yeah, I can take a first crack at that. I wouldn't say in our cases it usually has required electrical service upgrades. We have found that to be a limiting factor and have used the hybrid installation technique that I highlighted as a way around that. Also, a lot of times what appears to be a limiting factor when you just review the electrical capacity by looking at the panel sizes and breaker sizes with a more detailed load study, particularly if you actually put CTs on there and actually monitor the amount of power being drawn, you can find that you're way under capacity. My favorite personal story is I live in an all electric house, as I was mentioning, and had to install a 200 amp service because we were redoing the whole place. And but that was way delayed. And so on day one, when I moved into what is a 2-family house, it was meant to have 200 amp services. We ran the entire thing on a single 100 amp service. And we turned to test it on the day we moved in, we turned everything on, all the water boiling, all the dryers running, and we could only pull 50 amps. And it just goes to show there's a lot of safety factors built in. And so if you have an existing property and you actually monitor how much electricity you're using, sometimes you find what appears to be a limiting factor actually is not. And then if it actually is a limiting factor, then I would use a hybrid design to put in as much heat pump as you can, and then have the gas boiler carry the difference.
Anyone else have thoughts on this?
Yeah, there are also some devices, smart panels and switching devices that can be used to shuffle loads automatically that can potentially solve that problem. And furthermore, if you have a building that is maybe already set up for air conditioning with sleeves, probably okay in terms of your load on heat pumps. They're going to pull about the same amount of power. So there's a couple other considerations.
So there's a question that some of you started answering, but I think it's worth raising for the group. It says it's important to engage the residents in decision-making, particularly in LMI housing, but many residents are opposed to electrification, concerned about increased costs or potential impacts from power outages. Any thoughts on thoughts on this?
I'll start off. You know, one misconception is the power goes out, you'll still have your heat. That's not entirely true for natural gas, that is. Electric outage will affect gas systems as well. So it's, you know, when the electricity goes out, you're going to be losing your heat in both cases. Second, I do think it's a viable concern, the cost implications on tenants. And I think the beginning of this conversation could start around rate design. When we look at natural gas, there's rates for natural gas cooking, which are fundamentally different for natural gas heating. But generally, your electric rates aren't as varied for specific applications. And I think an ongoing conversation, both in California and New York, is going to be questions about what kind of rates should be created to not only minimize the cost impact on individual customers and landlords, but to also make sure that you attract the right usage of electricity, given the increased amount of electricity that we're going to be seeing through electrification, making sure that it's spread out at the right times and incentivized to be used appropriately. So I think rate design is going to be a big factor in that.
Just I'll add on that from the tenant standpoint, electrification will often bring them much more control and comfort than central systems that are poorly controlled and over which residents have little to no control. So that's a big selling point for residents.
Yeah.
If you eliminate, I'll just add, if you eliminate gas entirely, you can also eliminate those minimum monthly charges, you know, which a lot of times is, you know, I always remember when I lived in New York, I had a gas stove. I think I paid $10 or $20 a month for the hookup and about $1 a month worth of gas. So, you know, there can be that benefit too.
Really good point. So someone asked, this is to Julie primarily, can you discuss how hot and humid climates affect how building enclosures meet passive house infiltration rates?
Yeah, I think I answered that one in there, but I'll just say that, you know, the requirements for passive house, the air tightness it is what it is, right? So your fresh air supply is going to be designed to go through an energy or enthalpy recovery system. So it'll recover some of the humidity there, but on every project, whether it's in a hot, humid climate, we have dehumidification designed in. We don't put dehumidifiers in a unit. We sometimes have a bypass on the ERV. So if the air pre or post the ERV has not been dehumidified to the level we want it to be, then it goes through some dehumidification or cooling in order to bring the humidity down. So if residents open windows, it's harder to control the humidity. But if you know the building's airtight and the system's designed correctly, you shouldn't have an issue.
Any other thoughts on building envelope insulation? Okay, cool. So, and then there's this question that some of you have already engaged with, but the incentives available for electrification retrofits at the federal and local level. What do these look like for affordable multifamily housing units?
I can speak for California. I'm not aware of much of anything at the federal level presently. In California, there are some statewide incentives like the Low Income Weatherization Program, which we utilized on most of the projects I reviewed. And then there's also the BayREN in the Bay Area offers electrification incentives. And in Sacramento, SMUD is also offering electrification incentives. So it tends to be at the state and local level, in my experience.
In terms of federal, I think the only thing, Andy, out there, right, is the solar incentive, the investment tax credit. Each state has, you know, renewable energy credits to also helps offset renewable energy, which is can be really key when you're trying to electrify your building. Massachusetts, someone asked about that the leadership in this space seems like it's mostly low income developers, not market rate. And I think in Massachusetts, at least, the incentives are equal. Market rate developers can also utilize the incentive. So I know there's great incentives here that the utility gives based on maybe levels, you know, passive house. And then there's also, there was a grant that one of the Mass Clean Energy Center gave, design challenge grant for passive house. So we've been able to sort of move the market a little bit with some help, because the premium for passive house in a new market, we've been able to sort of offset, you know, bridge that gap with some of the incentives. I'm not that familiar with other incentives. I know there's some foundations in Illinois that the Illinois Clean Energy Foundation has some money. They have a pretty high bar for what performance you have to hit. But like Andy said, I don't know federal incentives for, you know, building better buildings or electrification or decarbonization, which would be nice.
So,
Go
ahead.
Sorry, I was going to add to that. In New York City at the state level, NYSERDA has a clean heat program, which provides incentives for heat pumps as well. And at the federal level, I know there's something with ground source heat pumps that's been tossed about, but I don't know the details of that. So that may come up.
Great. So that concludes our group discussion. Before we go, I'd like to do a final wrap up. I mean, first of all, again, thank you so much. This is an incredible session, and you guys have all done amazing work, and looking forward to what you're doing going forward. We'd like to highlight some of the resources mentioned today by the panelists, as well as some additional resources available on the Better Building Solutions Center. When the slides are made available, please click on each resource to learn more. The Better Building Solutions Center has over 3,000 solutions to help you find proven and cost-effective strategies to help you reach your energy, water, and waste reduction goals. Let's check out this video to learn more. Right. We'd like to invite you to attend our Better Buildings Summer Webinar Series starting in June. Partners will discuss some of the most pressing topics you're facing and share best practices and innovative new approaches to sustainability and energy performance. To register, go to the Better Building Solutions Center and click on Events and Webinars. Next slide. With that, I'd like to again thank our panelists, Jordan, Andrew, Julie, Rory, and Eddie, for taking the time to be with us today. We've launched a short feedback survey on Slido and ask that you please take a couple minutes to give us feedback on this session. Your answers will be totally invisible to other attendees. We rely on your feedback to design webinars, future summits, and more. The poll will be open until tomorrow morning. If you'd like to learn more about the resources discussed today, please check out the Better Building Solutions Center or feel free to contact me at the email shown. Thank you, everybody. Have a good rest of your day.